Hey guys, so this is Unit 6 video, well it's technically Lecture 2. We did Lecture 1 in class, okay, but I've also recorded the video for Lecture 1. So they're both available, but this is the first one that you actually have to watch because we won't be doing this lecture in class. Alright, so this is Unit 6, Lecture 2, okay, on collisions and conservation of momentum. Alright, so after this lesson, you should be able to describe the interactions of objects in either elastic or inelastic collisions. You'll be able to demonstrate collisions as a conservation of momentum. You'll solve for the final velocity, initial velocity, or mass of a system with both elastic and inelastic collisions. Okay, before we kind of continue on, I need you to remember from last time that momentum is a vector. Okay, it can be positive or negative depending on which way the velocity is. The second thing is that impulse is just a change in momentum. That's literally the definition of impulse. It's a change in momentum caused by some force applied over some time. Okay? And remember from last time, the longer the time, the smaller the force. That's what part 3 says. Okay? So before we get started, think about the following. Cars are actually built to crumple in an accident. This is counterintuitive because the car is typically useless after an accident. Why do you think the feature called the crumple zone is actually a safety feature? Okay, so take a couple seconds, pause the video, think about that for a minute, and then come back when you're ready. All right, so hopefully you had a second to think about that. The reason that the crumple zone is actually a safety feature is because it increases, let's write this down, the time of the collision. Right? It takes time for the car to actually crumple, and so in this picture up here you can kind of see it takes time for that car to actually crumple. So by increasing the time, we actually reduce the force on the car and incidentally on you, right? So by increasing the time of collision or by increasing that crumple zone, we actually decrease the force, which is the part that hurts you, okay? All right, so collision, there are two types, all right? There's elastic and inelastic. Elastic collisions are when two objects hit and they bounce off each other, so that after the collision, they're moving separately. So usually it looks something like this. Here's a car A, car B, okay? Let's say the car A is moving to the right, car B is moving to the left. After this is the kind of the before picture. Okay, and this is the after. And after they hit, right, so they hit like right around here. After they hit, car A is now going backward and car B is now going to the right. Okay, so they hit and they bounce off. I remember this because elastic is like, you know, like a rubber band is elasticy, it's kind of bouncy. So they bounce off of one another, okay? Now, inelastic collisions are the opposite. They hit and then they stick together after the collision. So they hit and they somehow get locked together, okay? So this would be like, let's say train car A, same situation, right? Car B, and let's say somehow their bumpers kind of get locked when they hit, and so when the thing is over, they are now one object, right? Even though they're two, but they're stuck together and they're moving together in one way or the other, okay? Whichever direction they're moving. Okay, inelastic means they stick and they move together after the collision. Knowing the difference between these two is very important, okay? All right, couple of notes here before we start doing some examples. All right, so momentum conservation, just like energy conservation, okay? This is especially important when you're talking about collisions, but basically it's where the total momentum just before the collision is the same as the total momentum after the collision, okay? Momentum before collision equals total momentum after of the whole system, all right? So here are the steps that I use and that I would suggest using when you solve collision problems, and I'm going to show you how we do this when I show you a couple examples, but here are the steps that I want you to take, okay? So 1, draw a before and after picture. They should look just like this, okay, just like this. Before and after picture, draw a dotted line between the before and the after. I've done that here. Before, dot, 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 after. Same thing here. Before, dot, 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 after. Okay? You're going to write MV for each object. So the momentum, you're going to write it for each object. Because the total momentum before equals the total momentum after, we need to know what was the momentum of car A before plus the momentum of car B before. That would be the total momentum before. The dotted line is where we put the equal sign, okay? And then we do MV for A and MV for B after. So total momentum of A after, total momentum of B after, and these two things should be equal, okay? But that's how we're going to set it up. So you're going to write MV for each object. Note that if it is inelastic, this is going to be MV plus MV equals M plus M times V, because they have one velocity together afterward, but they have both their masses combined. Okay, this will make more sense when we do an example. All right, write an equal sign where you have the dotted line and then solve the equation you just created. So these problems are actually kind of fun to solve because if you've drawn the picture correctly, the equation just creates itself. Okay, so let's do a couple examples here. Turn to the next page if I can. All right, we're going to do one of each type of collision here in the examples. All right, see if I can get this to a little lighter. Okay. All right, example 1. 2 train cars are traveling in the same direction. Sorry. A 6,500 kilogram train car is moving at a velocity of 5 meters per second. It approaches a second train car that has a velocity of 4 meters per second and a mass of 4,200 kilograms. When they collide, they will lock together and continue along the rail. What is their new velocity? So, before. They're traveling in the same direction, it says. Okay? So that means that the one that's going faster is going to be behind and then it's going to hit. So this one is the 6,500 kilogram and the velocity is 5. Okay? And then the second car moving in the same direction, its mass is 4,200 kilograms and its velocity was 4. Okay? And then afterward, they lock together. Okay? And they're going to continue moving in this direction. Okay? And I know that because both of them were moving in that direction to begin with. All right, so let's now write MV. This is my before picture, this is my after. Let's write MV for each one. So MV here is going to be 6,500 times 5. Okay, M times V. Plus, we have a second car with momentum before, 4,200 times 4. Do you see that this is the momentum of car, let's call this A, B. This is the momentum of car A plus the momentum of car B before, right? That's the total momentum before, equals total momentum after. Now after they are one object because they stuck together, so now their mass is actually going to be MA plus MB together, and then they're going to have some final velocity together. Okay, so MA was 6,500 plus 4,200 times their final velocity. Okay, now look how nice this is. This is actually an equation here, so let's actually simplify this a little bit here. So 6,500 times 5 plus 4,200 times 4 equals 6,500 plus 4,200 VF, right? So there's our equation that I created, okay? Plug it into your calculator. 6,500 times 5. I'm going to finish this over here. So that's 32,500 plus 4,200 times 4 is 16,800 equals 6,500 plus 4,200, 10700V, okay? Sorry, just kind of getting squished over here. This is their masses together. I'm going to add 32,500 plus 16,800. So this is 49,300 equals 10700 times VF, right? And then I'm going to take that and divide it by 10700, and I get VF is 4.61 meters per second. And that is their final velocity. Okay? So that's an inelastic example. Let's do an elastic example. So this is the bouncing off. These can be a little bit harder, but it's pretty much the same thing. Okay? 50 kilogram linebacker moving at 8 meters per second. So I'm just going to draw him as a box. I'm not going to draw real people. Okay? So this is the first guy. This is 50 kilograms. And he's moving at 8 meters per second. It doesn't tell me direction, so I'm just going to pick. Okay, I'm going to say he's moving to the right. He hits an oncoming 40 kilogram running back, so that means the running back's coming toward him. He's 40 kilograms and he's moving at 14 meters per second. Okay. The two collide and bounce off one another. Okay. So I'm going to assume then that the linebacker is going to go backward, and I'm going to assume that the running back is going to go forward. I'm going to say their masses stay the same, right? They don't trade mass or anything. Okay, and I'm going to say, let's say if the running back moves so backward, so this guy's actually moving at 10 meters per second backward. Okay, afterward, I don't know that guy's velocity after. Okay, and that's what we're trying to find. So let's set up MV. So MV for this guy is 50 times 8 plus 40 times 14. Okay, equals 50 times V plus 40 times 10. Oh, and you know what? I made a mistake here. We have to make sure we put negative signs in. This guy's moving backward. So this is actually negative 14. Sorry about that. Okay, so now let's plug this in. So 50 times 8 is 400 plus, actually it's going to be minus, right? 40 times negative 14, so minus 560 equals, I'm just solving this underneath, 50V. And I'm not going to put a negative sign in. It will come out negative if this guy is moving to the left. Okay, so don't put a negative sign in here. Just assume that the problem will give you a negative if he's moving backward. This was just a guess. Okay, and then this is 400. Okay, let's actually finish solving here. So this is negative 160 equals 50V plus 400. I'm going to subtract 400 to the other side. So I get negative 560 equals 50 times V. This actually just ended up being lucky here that this is working out this way. Okay, and we'll do negative 560 divided by 50. And we get the final velocity for the linebacker is negative 11.2 meters per second. So he is going backward. Okay, he's just moving a little bit faster than he was before because he got hit, right? So, and this guy had more momentum to begin with. All right, so that's his final velocity. But that's how you solve them. That's as simple as it is, right? MV plus MV equals MV plus MV. That's literally all it is. You just got to make sure your signs are good. And then once you've drawn this picture, you create the equation yourself, okay? Now, the last thing that can get a little bit tricky are these inverse collisions, which really is just a backwards inelastic collision, okay? So backward inelastic. And this is when you have something like where two things push off of one another. Okay, so a great example is like ice skaters when they first start moving. They kind of like, they start like this, right? They kind of start with their hands joined and then they push off one another, right? So they start connected as one person or one body, and then they push off, and so the after picture looks like this, right? This guy's going backward, and this guy's going this way, right? So it's a backwards inelastic. The same principles apply. You follow the same steps, okay? So example, a 50 kilogram ice skater, so here we are, at rest on ice, throws a 5 kilogram snowball. So let's say this is the after picture, okay? So the before picture would look like this. It's just her holding on to a snowball, okay? And then after, she throws the ball with a velocity, let's say it's going backward, but it's going 20 meters per second, okay? And the snowball itself is 5 kilograms. She is 50 kilograms, okay? And they want to know what's her final velocity. So before, they were just at rest, okay, on the ice. So they had a mass of 5 for the snowball plus 50 for the girl, okay? And their velocity was 0, all right? So the MV for before is mass 1 plus mass 2, so snowball plus the girl, so 55 times their velocity before, which is 0. which means that the total momentum of the whole system is 0, right? And so afterward, what's going to happen is this ball is going to go left, she's going to go right, and they are actually going to have the same momentum, but they're going to cancel each other out because of the direction, okay? But either way, same idea that we did before, mv for each object. So mv for the ball, or the snowball, is 5 times negative 20. Okay, don't forget it's going backward. mv for the girl is 50 times some final velocity. Okay, this side is 0 because they were at rest. This is negative 100 plus 50 vf. Okay, add the 100 to the other side. Be careful with your algebra here. Okay, and you'll notice that vf becomes 2 meters per second. Okay, so she's actually moving to the right at 2 meters per second after she throws the snowball. This is assuming there's no friction, right, on the ice. Otherwise, she would not move back so quickly. So friction kind of steals momentum, but we're assuming all frictionless unless you're told otherwise. Okay, so that's how you solve these, all right? You really do need to follow these steps. It makes it a whole lot easier, all right? Because once you have the picture, you have the equation, all right? All right, I think you are set. I'll actually give you the equations here real quick. So for elastic, it's always m1 v1 plus m2 v2 equals m1 v1 final plus m2 v2 final. Okay, that's actually the equation. But you don't need to memorize that, okay, because you are going to create it as you do the picture. For the inelastic, I'm just giving it to you so that you have everything you need, all right? This would be m1 v1 plus m2 v2 equals m1 plus m2 v final. Okay, so these are the actual equations that if you were to write them out, okay, but I do really insist that you do the picture thing and then just write mv for each object, and it will come out correct every time. Okay, that way you don't have to memorize equations. This is a lot of variables, okay, it can get kind of complicated. The picture thing works a little bit better. All right, see you in class.